In this video, we're going to take a look at binomial probabilities and the binomial probability distribution. First thing we want to probably talk about is, when does this come up? When is it appropriate to compute probabilities in a manner that is consistent with the binomial probability distribution formula? When do we use this? And basically, this is only used if the scenario in question meets the features of being considered a binomial experiment. So we want to talk first about features of a binomial experiment. Feature number one, there is a fixed number of trials. Denoted by the lowercase letter n. Okay, this cannot be an ongoing experiment. This has to be an experiment that is repeated a certain number of times, and then that's the end of the experiment. Okay, so in other words, if I sit down and roll a six-sided die at my dining room table 30 times, that would be a fixed number of trials, 30 times. Okay, so my n would be 30. If, on the other hand, I designed some kind of die rolling robot that's going to keep rolling the die forever and ever in perpetuity, that is not a binomial experiment. Okay, there has to be a fixed number of trials in order to do this. Number two, the n trials are independent and repeated under identical conditions. Okay, so to review independence, that means that the trials that come before can't affect the probability of what comes after. So that's what it means to be independent. The previous trials don't have an effect on the subsequent trials. And the trials ideally should be repeated under identical conditions. Identical here, is it going to be exactly identical? Probably not. But none of the important features of the experiment should change from trial to trial. So for example, if I'm flipping a coin a bunch of times, the trials would be independent. But to repeat them under identical conditions, I wouldn't want to start off flipping a quarter, flip that quarter for 10 trials, and then go, you know what, I'm bored with this quarter, I'm going to switch to a dime. Okay, if I've started with a quarter, I need to stick with that quarter. And ideally, I should be flipping them onto the same surface and all with my right hand. I shouldn't switch to my left hand. Okay, that kind of stuff, all of the important features. Feature number three, each trial has only two outcomes. We will call these success and failure. Okay. Here, a success is essentially the outcome we're interested in studying. Whereas failure is essentially not the outcome we're interested in. The reason I bring this up is that frequently when we're dealing with binomial probabilities, we use the word success and failure a little bit differently than we use them in everyday life. We're used to thinking about success as being a good thing or a positive thing, and failure as being a negative thing. And that's not the way that that works here. Success is simply the thing that we're interested in studying. It might actually be a negative outcome, but it will be construed as a success for the purposes of the binomial experiment. To give you an example, let's say that we have a particular brand of cell phone. We distribute it to 500 people. We're going to follow them for 20 years to see if any of them gets a brain tumor from using it. Well, if we're interested in people getting a brain tumor, if that's what we're trying to study, then if any of our participants get a brain tumor, that would be construed as a success, even though that is obviously not a positive outcome. Similarly, all of our participants who do not get brain tumors would be construed as failures, even though I think we would all agree that that's a very positive outcome to not have a brain tumor. So here it's important to not think of these as success being a good thing and failure being a bad thing. It's just a success is what we're interested in studying, and a failure is not the thing that we're interested in studying. Okay? So success and failure. Feature number 4. For each individual trial, the probability of success remains the same, and is denoted by the lowercase letter p. In these problems, it's going to be really important to emphasize that that p is lowercase, because we will also have an uppercase p in the binomial probability problems that will be referring to something else. So if you're talking about the probability of success on an individual trial, one individual trial, that should be a lowercase letter p. Also important to note that the probability of failure is denoted by lowercase letter q, and it's equal to 1 minus p because of the complement rule for probabilities. If probability of success is p, probability of failure has to be 1 minus p. And then what we're trying to do, those are the essential features in a binomial experiment. Typically what we're trying to do is we are trying to find the probability of a specific number of successes, which we usually call lowercase r. So r successes out of n trials. Okay, and that's the idea with these binomial experiments and the binomial probability formula. Let me give you an example. Let's say that we have an individual who's going to be taking a test, and let's say there are 20 questions on the test. And let's say that on each question there are multiple choice, so 4 choices per question. Only one of which is the correct one. Okay, so there are 20 questions, they've got 4 choices, one of which is correct. And let's further complicate matters by saying that this individual hasn't been to class in a very long time, and so they don't know any of the answers, and they are going to be guessing blindly on all of the questions. Okay, so that's their plan. They are going to guess blindly on all of the questions. 20 questions, 4 choices, only one of which is correct. So let's say the first thing that we are interested in is, as this student, as this hypothetical student, let's say we're thinking to ourselves, well, what's the probability that we might actually ace this test? How likely is it that we're going to get all 20 questions correct? Now, I think most of you looking at this are going, yeah, that's really not all that likely. But let's actually quantify it. So what is the probability of getting all 20 questions correct? Okay. So, first of all, we need to check our list of features to see if this meets the criteria of being a binomial experiment. So first of all, are there a fixed number of trials? In this case, yes. They get 20 questions that they're answering. Okay, so in this case, n is equal to 20 because there are a fixed number of trials. 20 questions. They're going to repeat this guessing process 20 different times. Are the results of the trials independent and repeated under identical conditions? Well, presumably so. Identical conditions, it's going to be the same day, the same testing situation. Are they independent? Chances are your guesses on previous questions are not going to affect your guesses on subsequent questions, so we can assume that those are independent. Does each trial have only 2 outcomes, success and failure? Sure. You either get the question right, or you get it wrong. If you get it right, that's a success. That's the thing we're interested in. If we get it wrong, it's a failure. For each individual trial, the probability of success remains the same and is denoted by lowercase p. Probability of failure is q. So in this case, we also need to identify lowercase p and lowercase q. Lowercase p, the probability of success on any individual question. Since each question has 4 choices, only one of which is correct, p is equal to 0.25. They have a 25% chance of guessing correctly, which means that q, their probability of failure, is 0.75. Okay. So it does meet the criteria for being a binomial experiment. We know our parameters. And at this point, the book goes over a couple of methods for doing this. There is a binomial probability formula for calculating binomial probabilities. Historically, they were also computed using a binomial probability table, which also exists in your book, but we're actually going to take advantage of the calculator program that does binomial probabilities. So first, we need to take what's written here in English and convert it into its formal equivalent. We need to use correct notation. Since we are trying to find a probability, we're going to be using a capital letter P to denote that we're finding a probability. And then since we're getting all 20 questions correct, that would be R is equal to 20, R being our number of successes. So we want to know what's the probability of exactly 20 successes. Now, anytime you're dealing with a probability problem that has an exactly equal to right here, in your calculator, the program that you're going to use is something called Binom PDF. It stands for Binomial Probability Density Function. This is the calculator program that computes binomial probabilities for us. And I'll show you where it is on your calculator in just a second. And then inside a set of parentheses, you will need to put 3 inputs. Specifically, what your calculator wants are the values of N, P, and R. So just think National Public Radio. And it wants them separated by commas. So in this scenario, when we want to know what's the probability of getting all 20 correct, we had 20 trials. Probability of success on any given trial was 0.25. And we want to know what's the probability of getting all 20 correct. So our R is equal to 20. And this is what we will enter into the calculator to get that to come up. Now in your calculator, this calculator is running the old operating system. If you have the new operating system, it'll be slightly different. But you want to go into, see this button here, VARs, and it has DISTR above it, D-I-S-T-R. That's your distributions menu. So we will press second and then VARs, and that'll take us into this distributions menu. And what you're looking for is going to be way towards the bottom of the distributions menu. Right here it is, Binom PDF. There's also a Binom CDF. Don't select that one. We'll talk about it in a minute. Okay, so Binom PDF. We want to select that. And then we just want to put in our values. Now, if you have the new operating system, instead of this screen, up will come a screen that asks you for trials, probability of success, or P, or something like that, and then X. Basically, it's asking you for N, P, and R in exactly the same order. So you would put all of those into your screen. So N, 20, comma, 0.25, comma, 20, close your parenthesis, and press enter. And here you can see we get something that at first, if you're not paying very much attention, looks like it's a huge probability, 909%, 9.09. But way over here is that scientific notation that maybe you haven't seen in a while. This is about 9.09 times 10 to the negative 13th. Okay, so the probability of this occurring, 9.09 times 10 to the negative 13th power. That is a decimal point, 12 zeros, and the 909. Okay, this is not pretty. The likelihood that by guessing blindly you're going to get all 20 questions correct is about 0. It's not actually 0. There is a very, very tiny chance that you could get them all correct, but it's so tiny that you might as well not even consider it. This is basically impossible. Okay, so that's how we use our binom PDF. Now at this point, our student, understandably, I think, is getting pretty disheartened. They're like, okay, so I can't ace it. So then maybe, continuing on with the same problem, maybe this time they think, okay, well, what's the probability that I'm at least going to get a 70? Like, I can live with a C- or above. So maybe they say, what's the probability of getting 14 or more correct? Okay, because 14 or more would represent, well, 14 out of 20 is 70%. So 14 or more would be a 70% or above. So maybe we think, okay, we can live with that. Notice that this is a fundamentally different type of question. This is not an exact. We're not getting exactly 20 correct or exactly 14 correct. We're talking about 14 or more. So one way to do this, if you're thinking about probability, again, we want capital P, 14 or more correct. If I'm thinking about my lowercase letter r here, that's a greater than or equal to 14. And certainly what you could do is you could find the probability associated with exactly 14, 15, 16, 17, 18, 19, and 20 and add them all up, and that would work. But there is a way to do this in the calculator that's much faster. The problem is, if we want to do this in the calculator, we're going to need to use binom CDF. And binom CDF is a really fussy program. It has to have a less than or equal to sign here. It will not tolerate a greater than or equal to sign. So the first thing I'm going to do is, using the complement rule from our probability chapter, I am going to say that the probability that r is greater than or equal to 14 is 1 minus the probability that that does not occur. In other words, 1 minus the probability that r is less than 14. Okay, that's coming from that complement rule. Probability of A complement is equal to 1 minus the probability of A, and these two are opposites. Okay, the opposite of r being greater than or equal to 14 is r being less than 14. Now at this point, it's so tempting to just do a happy dance and go, okay, I can use binom CDF now. But your calculator needs to have a less than or equal to. It's very, very particular. This has to be a less than or equal to in order to use binom CDF. So I think, okay, 1 minus probability that r is less than or equal to what? Well, if you're thinking about numbers of successes, and we want less than 14 successes, that would be 13 or fewer successes, less than or equal to 13. And this statement, probabilistically, is identical to this original statement. It's just a different way of phrasing it. And now that I have a less than or equal to, I can put this thing in the calculator. Okay, so what I'm going to put in the calculator is 1 minus binom CDF. And again, it still wants N, P, and R. So we have 20 trials on this test. Probability of success is 0.25, and this time the R value is 13. And that's what we're going to put into the calculator. So we have 1 minus, we put that right out front, second vars, to go to the distributions menu, find binom CDF, and select it, 20, comma 0.25, comma 13. Okay, so this is better, right? 2.95 times 10 to the negative 5. Definitely more possible than getting them all correct. 2.95 times 10 to the negative 5. But it's still a decimal point, 4 zeros, and a 295. It's still basically a 0% chance. It's a lot more possible, but it's still not looking good. We are not, most likely, going to get a 70% or better on this test. So now our imaginary student gets really upset and they think, oh man, so what's the probability that I am likely just going to totally tank? Okay, so maybe this time they're wondering, what is the probability of getting fewer than 10 correct? Right? Maybe they're thinking, okay, I could live with myself if I get at least half, if I get 10 or more. So what's the probability that I'm actually going to get less than 10 correct? Because they're thinking, man, that would just be horrible. I really don't want to do that. Okay. Again, probability, big capital P, fewer than 10 would be R is less than 10. Notice there's not an or equal to because it doesn't say 10 or fewer. It says fewer than 10, meaning literally less than 10 correct. Now into the calculator, again, I need to have a less than or equal to here to use binom CDF, and right now I don't have that. But unlike the previous example, I'm not going to need to use the complement rule because I don't need to get the inequality sign to flip around. I just need to get an or equal to underneath it. So if I have less than 10 correct, then I must have 9 or fewer problems correct. I can just knock that number down by 1. And that's what's going to go into binom CDF. Okay, 20 problems, probability of success 0.25, and 9 is the value for my probability statement. So then into our calculator, again, distribution menu, scroll and find binom CDF, 20, 0.25, 9. And we're looking at about, if we rounded this to 2 places, about a 99% chance. There is almost a certainty, it is almost a certainty that we're going to crash and burn on this test. We are going to get fewer than 10 correct, which would represent less than 50%. Okay, very, very sad. So a couple of takeaways here. First of all, this is how binomial probabilities work in your calculator. Second of all, always a good idea to go to class so that you don't have to guess blindly on multiple choice tests. Really improves your odds quite a bit. Okay, let me give you one last thing that'll be really helpful with your binomial probabilities, and that's a little cheat sheet about how to do those conversions. So if you start with a statement that you want the probability that the number of successes is exactly equal to some numeric value, that's when you just use binom PDF n, p, whatever that number is. Okay, that's just straight up, if there's an equal to, goes right into binom PDF. If there is a less than or equal to here, that goes straight into binom CDF, n, p, whatever that number was. If we have a less than instead of a less than or equal to, we don't have to do a 1 minus out front because, again, we don't need to get this to flip around. We just need an or equal to underneath it. So that's going to be binom CDF n, p, whatever that number was, minus 1. We'll have to knock that number down by 1. That makes the or equal to show up. If we have an r greater than some number, that's when we have to do 1 minus to get this greater to, to become its exact opposite, which is a less than or equal to. So n, p, whatever that number was. If you start with a greater than or equal to, this is actually the one where you have to do the most work. You have to do a 1 minus out front, binom CDF, to get this to become its opposite. So instead of a greater than or equal to, you would have a less than. But then you need to get a less than or equal to, so you're going to have to knock whatever that number was down by 1 to get the or equal to come back. And so these are all of your different conversion rules so that you can get it into the appropriate form to use in the calculator.